After this one again, that call me.
Okay. So we're gonna start off class today by remembering what depolarization is and thinking about what happens when sodium channels open. Next, I'm gonna ask you to think about what happens if a potassium channels open. You can write this in words. I like drawing, so when I explain this and review this with you right now, it's probably going to be a little bit of a drawing going on, but I'll give you a minute to do this. I also do want to remind people verbally now that like every weekend, we do have a quiz that is due on Monday. So that's up, that's open. You can find it if you go directly to quizzes. You can find it if you go to the content tab, quiz 5. So you'll be asking you some stuff about membrane potential, some stuff about the sodium potassium pump, and a little bit about our graded potentials that we've moved into on Wednesday. We'll be talking a little bit more about today. So I'll give you a second. Think about depolarization, sodium and potassium channel. You can keep working. I'm just going to start drawing our starting point. This is what we've been talking about this week. We're going to start this first one thinking about sodium channels opening, right? So what I drew so far was our setup, things we know already, right? So we know that our typical cell, our typical neuron has a membrane potential of -70 millivolts at rest. That's our resting membrane. We've been talking about how that gets set up, how the sodium potassium pump is involved in that, setting up concentration gradients and some electrogenic action directly on that negativity of the cell. And we know that under our initial starting condition for a neuron, we have relatively high permeability to potassium. Those are my purple little lines are my leak potassium channel. We've got more potassium leaking than we have sodium leaking, which is part of why we are at specifically that number, -70 for our resting membrane potential. Okay, so when we're thinking about depolarization, which we defined last time as something that gets us closer to a threshold for setting off an action potential, something that makes our cell less negative, so it moves us closer up to 0 as well. So our threshold is going to be slightly closer to 0 than our starting point. So that's our depolarization direction, up, right? Okay. So what is happening with our depolarization is that we have more sodium channels opening, right? Okay, so we have sodium, our original driving force on sodium. So we have both a chemical and an electrical driving force pulling sodium into the cell, right? That's the direction sodium is always going to want to go if we're at our resting membrane potential of -70. And we can double check that and know that because we have this really positive equilibrium potential for sodium. The direction that sodium wants to go wouldn't reverse until we got to like +70, right? So we got above that equilibrium potential. So this is no problem. We know sodium wants to come in. Part of the reason we're not up in that positive range is this low permeability to sodium, right? We've only got this one little door in the membrane. So in this situation where we're depolarizing, what we have happening is we're opening more sodium channels, right? So when we have more sodium channels, this means that now more sodium can get through, right? So it already wanted to go through, couldn't because it didn't have quite enough space, right? And now we get more and more and more sodium coming into our cell. Okay. So without any numbers of amount of sodium, we would know exactly what number we get to. I'm not going to make you do calculations here, but as we have these positive charges moving into the cell, right? This means we're depolarizing, so we're going to become more and more positive, right? Less negative. So we go to -65, -60, maybe -55, right? We're going to be going up, right? So that's what our depolarization is with sodium, right? So our membrane potential is going to go up from that -70 value as we increase the permeability of sodium. So that's our depolarization and why this has to do with sodium specifically. Whenever we think about sodium, flip side, we think about potassium, right? Flip side of the sodium potassium pump. Here's the potassium part. Sodium and potassium are going to be having essentially opposite actions on our membrane potential. So they want to go opposite directions relative to the inside or outside of the cell. And they're going to have opposite effects then on the membrane potential. Okay, so starting with that same resting membrane potential, starting with that same distribution of potassium, sodium permeability, we're talking about something that opens up more potassium channels. Okay. So we know already under normal conditions, there's a force for potassium to leave the cell, right? And we know that because potassium won't stop moving unless we get down to -94, right? The direction that gets us closer to -94 is if we have those potassium ions moving out, right? So at this point, we can see that that -70, that negative charge should be pulling our potassium ions inward, right? So the electrical driving force would be in. So the fact that potassium is going out, the fact that that's our electrochemical driving force direction, means that our chemical driving force is really strong, right? So this is due to that concentration gradient that we set up using our sodium potassium pump. Okay, so we know our direction. So when we open a potassium channel, right, we're going to allow some more potassium to leave. The force on this is relatively weak compared to the sodium, right, because we don't have that much of a difference between our potassium equilibrium potential and our resting membrane potential compared to that huge difference for sodium. But we do still have a little more potassium leaking out. All right, so in this case, where we opened up more potassium channels, we'd start to get more and more negative as those positive charges leave the cell, right? So those positive charges are leaving the cell. So we're going down to negative 75, negative 80, etc., until we get to negative 90-ish, negative 94, depending exactly on the concentration gradients that we set up. So the word for this is hyperpolarizing. So this is hyperpolarization. Questions about this setup that we've created using our sodium potassium pump to set our resting membrane potential at negative 70, set up all these gradients, set up all these charges so that we have a stable, predictable direction that we know sodium wants to go, direction that potassium wants to go. We know kind of what that's going to do if you open a channel. Cool. So that's fundamental to how all of this stuff is working, right? So when we left off, we were talking about graded potentials. So when we think about graded potentials, at the top of this unit, we're thinking about them as initial reactions to stimuli, small changes to the membrane potential, right? And this is going to be directly linked to this idea of ions moving. Fundamentally, to change the membrane potential, we've changed what ions are coming in, what ions are coming out. So ultimately, we're not going to get into the details of like how it happens, but our gradient potentials would involve a sodium channel, a potassium channel, potentially some other channels that we won't talk about, opening to slightly change our membrane potential. Okay. When we left off, we were talking about the fact that graded potentials can sum together. And we mentioned this idea of the fact that they can sum over time or they can sum over space. Okay. We're going to think about that temporal summation first. Okay. So what we're thinking about when we think about summation, I'm going to draw a really bad neuron, actually. Okay. So I'm going to be doing just the soma, the axon hillock, a little axon, and then I'll give it some like spaghetti fingers at the end for our axon terminals. Okay, cool. All right. And I'm going to give us 3 of them, so we have our 3 different time points. Unlovely drawings, but this is why we care about this summation stuff. All right. So when we're thinking about temporal summation, we're thinking about a stimulus that happens multiple times. So the same stimulus, just firing like once, pausing a beat, then firing again. So I'm just going to draw us a little red arrow for our like poke. That's our stimulus. Okay. And we'll have another poke at time 3. Okay. So when we say that we have temporal summation, we're saying that if we start with a cell at negative 70, let's say the stimulus is creating a graded potential in that depolarizing direction. Okay, so it's going to get us closer to 0, closer to our threshold. Okay, so essentially, we're thinking a stimulus that somehow opened a sodium channel, left some sodium. That's how we can get the depolarization. Okay, so for time 1, we have our beginning starting point of negative 70. All right, our stimulus comes in, opens some sodium channels. I'm going to cross this out now, right? Immediately, we're going to see a slight change. Let's say we get to negative 65 here. Okay. So I changed the membrane potential in this local area by 5 millivolts in this example. Okay, so that was what the stimulus did. Over time, this fades, right? Our sodium potassium pump is still working, restabilizing concentration. We have these leak channels, right? The resting membrane potential is the resting kind of set point, unless we kick off an action potential. So this effect is going to start to fade off over time. So let's say at time point 2, this has started to fade, so we've started to go back down towards that -70. Let's say we didn't get all the way there yet. Okay. So at time point 2, we're going to be, let's say at like -68, right? So that's going to be our starting point for what happens when we have the stimulus come in again, right? So temporal summation. The idea is that our effect of the stimuli is going to kind of add together, right? So now as we have this temporal summation, we're going to have that same effect, let's say, that difference in 5 millivolts when the stimulus comes in, right? But now, instead of only getting to -65, right, because we're already partway there, doing my number line in my head, okay? So now instead of getting to -65, right, let's say we get to -63, right? I didn't do that math right. Anyway, we get a little higher. Okay. So we get a little higher, a little closer to threshold over time. So that's all temporal summation is that eventually you can get one little bump, start to fade off, another little bump, start to fade off, and eventually you might hit your threshold in this way. Okay. Questions? I won't make you do any actual numbers when I'm asking you questions about this. So these are just kind of like fake numbers to understand the idea here. Cool. So this is just like getting poked over and over again in the same spot. Okay. In our spatial summation, we're not thinking about time anymore. We're thinking about space, right? So we're going to have our soma again, our axon hillock, and our axon terminals at the end of the axon. Okay. So now we're thinking about two different stimuli coming in from different locations. Right. So here we have one stimulus. Here we have another stimulus. Right. And each of these stimuli has an effect, right? Okay. So if we're starting at -70, right, what can happen is that as we have ions start to flow in each of these locations, so I'm going to give us some positive ions here for our sodium flowing in, right? We have some positive ions flowing in at this second location as well. So I'll get the numbers the same. Okay, I'm drawing 5 at the original site. They're going to start to spread out, right? So we'll see some over here, spreading to the side, right? Same thing is happening here. So basically what can happen is that in the center of our two stimuli, we're going to have adding together effects from our multiple stimuli. Again, we're not going to do direct numbers on this, but this is what we're thinking about when we're thinking about spatial summation. I should clarify, the reason I had my numbers going down in the middle in the temporal summation and I have these ions moving down a little towards the center here, that is one of those definitions of graded potentials, one of their qualities is that they're decremental, that they decay, right? So over time they fade, and also as we move farther away from the location where they hit the cell, they fade a little bit. So that was not related to the idea of spatial summation directly, but just related to how graded potentials are in total. Okay. So these are the two ways that we can have additive effects for graded potentials. Questions? Cool. Awesome. It should not be that complicated, so that's great. Okay, so we can add together graded potentials. It's great because we want to get towards our threshold for an action potential. Okay. So when we think about our action potential, we're going to want to remember how we describe the directions of changes relative to our resting membrane potential. Okay, and we're going to have these happen in a specific order in our action potential itself, but the words themselves are really just corresponding to what direction the membrane potential is going. So our resting state, our resting potential. So if you measure a neuron at rest, your reference point is going to be -70. When we see depolarization happen, that's going to be in the up direction. So up towards 0, and we are, for our purposes, going to keep this depolarization word anytime we're going kind of up direction because of how neurons happen to work. Okay, but it's defined for this fact that we were originally getting 0. The depolarization is up, okay, membrane potential getting higher. Hyperpolarization would be down, so getting farther away from 0, usually towards that equilibrium potential for potassium. Okay. And we'll also see kind of additional terms thrown in here when we talk about action potential. That if we have the depolarization happen, right, so if we go up, set off an action potential, eventually we're going to have to get back down to rest. When we are getting back down to rest from a change, we're going to call it repolarizing, right? So we were polarized, we depolarized, and now we repolarize. So these are our directions away from rest or towards rest. So I want you to predict, based on what we've been talking about, how this relates to our ions, right? So when we're going to see our action potential, we're going to have an ion responsible for the depolarization phase. When we have repolarization, so coming back to rest, we're going to have a different ion in charge of that. So go ahead and answer this question. Take another couple seconds. And we'll take a look. All right, cool. Yes, it is our friends sodium and potassium. So sodium and potassium are driving lots and lots of things in all our cells, all our tissues, including our action potentials for our neurons. Okay. So depolarizing, sodium flows in, we get to threshold closer to 0, and then we're going to spike up to +30 actually. And in order to get back down to rest, in order to repolarize, we're going to open potassium channels to pull us back down towards those negative numbers, towards that equilibrium potential for potassium, although we don't get quite all the way there. Okay, so that's based on the directions that we've just set up. We understand why they want to go those directions based on their electrochemical driving forces. You have this link later in your slides, but I heard that this was maybe helpful. So we're going to take a look at the action potential and how it looks, and then talk about how we understand it.
Over long distances by generating and propagating action potentials. Most action potentials originate near the axon hillock of the cell body in the initial segment of the axon. It then travels the entire length of the axon. A closer look reveals that during an action potential, voltage-gated channels open and close, altering the permeability of the plasma membrane to sodium and potassium ions. A threshold stimulus changes the shape of the voltage-gated sodium channels, causing their activation gates to open. This event marks the beginning of phase 1 of the action potential, known as depolarization. As sodium ions diffuse into the axon, the membrane potential becomes less negative. This causes more voltage-gated sodium channels to open, and the membrane potential soars to plus 30 millivolts. At this point, two key events occur. The inactivation gates of voltage-gated sodium channels close, and voltage-gated potassium channels open. These two events mark the beginning of phase 2 of the action potential, known as repolarization. As potassium ions diffuse out of the axon, the membrane potential becomes negative again. However, the membrane potential continues in the negative direction, going beyond the resting state of minus 70 millivolts. This marks the beginning of phase 3 of the action potential, known as hyperpolarization. During this phase, voltage-gated potassium channels close and all voltage-gated sodium channels are released from inactivation. By the end of this phase, ions move through weak channels only, and the membrane potential returns to the resting state of minus 70 millivolts. The neuron is now ready to fire another action potential. Summary: generation of an action potential. A threshold stimulus opens voltage-gated sodium channels. Sodium ions diffuse into the axon, depolarizing it to plus 30 millivolts. Voltage-gated sodium channels close, and voltage-gated potassium channels open. Potassium ions diffuse out of the axon, repolarizing it to a negative value. The membrane potential briefly hyperpolarizes. Voltage-gated potassium channels close, and the membrane returns to the resting state of minus 70 millivolts.
So that is literally the full picture of what we're going to try to understand. So we're going to look at pictures of this over and over again and talk about it from multiple directions, but that's kind of the long and short of it. Okay, so as we think about the action potential, we're thinking about firing off a signal to another neuron or potentially to an affected organ out in the body. Talk about what those are later on. And we're doing this by opening and closing sodium and potassium channels, changing the membrane permeability to sodium and potassium at different time points. So we essentially have this wave of charge flowing down the axon of the neuron. Okay, so as we're thinking about the different types of ion channels that you see in a neuron, I made you this kind of summary table of all of the ones that are there, because we're going to want to be able to compare which types of channels do what and where they are. Okay, so the ones we've been talking about up until now, up until today, we've mostly been talking about our leak channels. So the leak channels were the ones that were responsible for setting that resting membrane potential. They're always open. 25 times as many leak channels exist for potassium than exist for sodium. And we see them everywhere in the neuron. So you see them in the dendrite, you see them in the soma, you see them in the axon helix, the axon, and the axon. That's because we want all those areas to be able to get back to negative 70 when the neuron's at rest and not doing anything. What we have been talking about in a kind of sideways way just now, when we've been talking about graded potentials, is often these are going to be ligand gated channels, although some of them may also be voltage gated. But what a ligand is something that binds onto something else, right? So we're imagining a channel that's closed initially, right? And then just like an enzyme changes shape when something binds onto it, if we have a ligand, like say a neurotransmitter, bind on to this ligand-gated channel, it may open, right? So that changes the shape of the protein. That might switch to an open state briefly before we have that ligand break off and float away. Right, so we've just opened a channel, so we can now change the amount of sodium and potassium moving across our membrane. Right, so when we say a stimulus caused a graded potential, this is usually the mechanism for that, right? Is through these ligand-gated channels. So correspondingly, you see them in the areas of the neuron that are adapted for receiving signals, right? So our dendrites, those little kind of hairs on the head of the neuron, those are for drawing in signals from neighboring neurons. So they're going to have these ligand-gated channels that are often binding neurotransmitters. The cell body, the stoma, is often also going to be receiving some of those signals. So it would also have ligand-gated channels able to respond to things like neurotransmitters there as well. What we're going to need to understand now for our actual action potential are our voltage-gated channels, right? So when we talk about something hitting threshold or not, the reason we're talking about that is that voltage-gated channels at the resting membrane potential are closed, right? We're going to have two types, potassium and sodium voltage-gated channels. What happens with these channels, right, is that at -70, they're closed. But when we hit a specific voltage, they're going to open, right? And they do this in part because they have gates that are initially closed and then open up. Depending on whether we're talking about a sodium or potassium channel, we might have one or two kind of gates. And that's what we're going to get into with the rest of today. Okay. So these voltage-gated channels that we see are going to exist specifically in the areas, they're going to be concentrated in the areas where we are sending off our action potential. That's where we care about the most. Okay. So they're opening and closing when the membrane potential changes, specifically when it gets to the threshold value, right? That's why we've been trying to see, is the graded potential summing up to that threshold or not? When we hit that voltage and it causes them to open, this is going to start the action potential in the axon hillock. So we have lots of extra voltage gated channels in the axon hillock. And we see lots down the axon as well, because that's like our communication highway. We will see some of them elsewhere about, but that's where they're most important, because that's where our action potential is really happening. Finally, when we get to the end of this unit and talk about synapses, we'll add on another ion. So calcium is Ca2+, okay? And calcium channels are going to be related to our release of neurotransmitters at the end of our action potential. So we'll get there when we get there, but figured having it all together for you will make it a little easier to study. So that's the big rundown. So questions about these types of channels, and particularly since we're moving on from the leak channels and the ligand-gated channels now, any remaining confusion about those? We'll break into the voltage-gated channels then, which are the big ones. Okay. So we're going to start with sodium. All right. So voltage-gated sodium channels can be particularly lots of them in our axon hillock, in our axon, and what they're doing is waiting until we get to a membrane potential of -55 millivolts. We get to that membrane potential by a series of graded potentials adding together, either over time or over space. If we get to -55, that's like the on switch for our sodium channel. Big picture, voltage-gated sodium channels open at -55, which means lots of sodium can come in, and our membrane potential rapidly depolarizes. We shoot way up when we open voltage-gated sodium channels. Okay. When we get to +30 millivolts, this is the point at which those voltage-gated sodium channels start to close back up again. So they're not open forever. They don't stay open all the way up to positive 60, which is why we don't really get higher than positive 30 when we're looking at our action potential. So they're just open for a period of time and a specific range of membrane potentials, but they get us really far away from the resting membrane potential while they're open. But we're going to look closer at that opening process. Okay, we've got some complicated pieces for our sodium, our voltage gated sodium channel. So the shape of this channel, when we start out at rest, the resting membrane potential, we've got the typical kind of outer structure, right? So we can kind of see where there's going to eventually be an opening in the center, right? A kind of tube doorway structure. Sorry, I'm trying to figure out a color that will show up. Might be none of them, okay, but you can see it. Okay. But when we're at that resting membrane potential of -70, right, no sodium can get through because we have this activation gate in the center that's closed. Here's our activation gate. So you can see these kind of like lips closing over that sodium channel here. So the resting membrane potential, these are closed because the activation gate is closed. So no sodium is coming in. Okay. We'll get to what this parenthesis bit means in a little bit. When we hit the threshold, we depolarize the threshold. So our membrane potential changes, we get to -65. That's our trigger. That's when our activation gate opens. Right? So our activation gate is open now. Great. We got a passageway all the way through our channel, so sodium can flow through. Okay. Here's where it gets a little bit tricky. So there's a little bit of a time delay. And then the next part of this voltage-gated sodium channel comes into play. So when our voltage-gated sodium channels close, it's actually not first that activation gate that's closing. We don't just have one gate in the center that opens and closes. We have two gates. So our activation gate was open. We got to -55. And after about a millisecond, when we get to +30, this bottom piece starts to move. So this bottom piece is your inactivation gate, and it swoops and closes over our channel from the bottom. Right, so we can see now we're closed over from the bottom. So sodium can't move through, but actually at this point in time, right, our activation gate is still open. So as we're repolarizing, what's happening is that our activation gate may still be open, but we're not going to have sodium moving through because this inactivation gate has closed the other side of this channel, right? So it's blocked the further progress of the sodium across this membrane. And what happens to be true about the inactivation gate is that it also has its own like time delay, kind of. So for a certain period of time, once those inactivation gates are closed, think of them as kind of paralyzed, right? So they're going to be incapable of opening back up. They're going to be stuck closed, paralyzed closed, jammed closed in the sodium channel until we get back to the resting membrane potential. So they're going to be jammed in there until we get back to rest. As we get back to rest, those inactivation gates swing back open, but at the same time, the activation gates close back over. So this is all happening as we're resetting to our original resting potential. So we have these two pieces that we have to think about. So the activation gates first need to open. Then we have both our gates open, the activation gate and the inactivation gate need to both be open for sodium to come in. And then sodium gets blocked, but what it's getting blocked by at first is the inactivation gate until we reset to our starting point. So here we have that kind of in words. We'll go through it, but that's what we're trying to understand, right? So we have two types of gates on those sodium channels. We have that activation gate and we have the inactivation gate. So the activation gate is the one that is first responding to that voltage, and it just opens as soon as we hit the threshold, right? No time delay on that, just voltage opens it. Okay. So it opens at our threshold, and it remains open through the depolarization phase of our action potential. It's going to stay open as we peak up to positive 30. And it actually is working kind of as a positive feedback loop. So as soon as you have one voltage gated sodium channel fully open with that activation gate open, the neighboring voltage gated sodium channel is now going to notice all those sodium ions flooding in and slightly affecting the membrane potential in its little chunk of membrane. And so that's going to get the neighboring one to threshold and open it up on and on and on like dominoes. The inactivation gate, so that bottom gate, partially responding to the voltage, so partially to that threshold, but it's doing it with a time delay, right? So we have this 1 millisecond before it starts to swing close. So it was open at rest, right? It was open at rest, activation gate open. They're both open for about a millisecond. Then that inactivation gate swings closed, so sodium can't get into the cell anymore. So what was happening here in terms of like our phases of the action potential is that during our depolarization phase, so our first phase of our action potential, we're going to see those inactivation gates open, right? But at the end of our depolarization phase, they're going to start to close, right? So at the end of depolarization, these are starting to close, which is why we slow down our rise, and then that's what's going to help tip us over into our repolarization phase. Our other type of voltage gated channel is for potassium. These ones are easy. They just have one gate. We don't have to name it. So potassium voltage gated channel is just open or closed. We don't have to worry about activation gate, inactivation gate. It just has that one little piece, basically. So around that peak of the action potential at 30 millivolts, that's when our voltage gated potassium channels open. And we know that we've got our setup for potassium with the electrochemical driving force pointing out, still pointing out when we're at positive 30, right? In fact, we're even farther away from our equilibrium potential for potassium when we get to positive 30. So that force on potassium has gotten stronger. And so when our potassium voltage gated channels open at positive 30, potassium rushes out of the cell following its electrochemical gradient. So this is really the bulk of what is making our cell repolarize. So it doesn't keep going up because the sodium channel is closed, but it actually goes down because potassium starts leaving the cell. So that starts to repolarize our membrane potential, leading to the second phase of our action potential. So for those voltage gated channels for potassium, we got just one gate. Depends on the voltage. So we're getting to positive 30 around that 1 millisecond mark. So we can think of both voltage and time when we think about our potassium voltage gated channels. We think of this as a mechanism for negative feedback, right? Because we had a change in one direction, and now we're having a change in the opposite direction, which is our negative feedback typical of homeostasis. Okay. So just making sure that we understood what I was saying about those gates. Go ahead and answer. So at rest, our sodium ions have an open inactivation gate. Is that true or is that false? Cheating to look at the pictures, just keying you in on something that's important to understand and notice for yourselves. you're answering, put in your votes now. Let's take a look. Okay. Cool. This is true, right? So at rest, right, we got membrane, we've got our channel. Right, so here are the walls of my channel. All right, here are the walls of my channel. Okay. The reason sodium can't get through at rest is that the activation gate is closed. So that like first cell door is sealed over. So sodium can't get through. But at the bottom, that inactivation gate is still open. Okay. So this means that as soon as the activation gate opens, we can get sodium in. We don't have to worry about both of these doors, just this top one. All we have to do is open the activation gate, which is why it's called the activation gate. Right? So the activation gate, once it's open, everything's through. That's kicking off our action. So this is ultimately what we've been trying to understand and what we'll continue to go through. So we're looking at the action potential, right, which has a depolarization up to positive 30, repolarization down, and then we actually hyperpolarize a little bit. We go past our rest until we restabilize at our resting membrane potential. And the reason we're doing this is that we are opening and closing these voltage-gated sodium and potassium channels. The ultimate effect of that is an effect on the permeability of the membrane. So that's what these PNA and PK are telling you about. Right, so we can see that at the beginning of the action potential, the permeability of the membrane to sodium has gone way up, right? Because we've opened all those activation gates on the voltage-gated sodium channels, so lots of sodium can come in. That's what permeability is, the ability to cross. And then as those inactivation gates swing closed, permeability of the membrane to sodium goes down. We got a bit of a time delay for the potassium, right? So we have slightly more permeability at rest to potassium than sodium. We know that that's because of the number of leak channels, right? Then as we're in that repolarization phase, we can see that's when our potassium voltage-gated channels opened, and eventually they close, letting us get back to rest. Right. We'll go through that in further detail next week, but that's the short of it. Okay. So remember to do those quizzes, and remember to tell me what you were or weren't confused about. Okay.